Talk about drawing 3D structures using the VSEPR method. That's VSEPR. That stands for valence shell electron pair repulsion. And the idea here is that these electron pairs, which we are going to call electron domains, repel each other because they are all negatively charged. And when they repel each other, they try to get as far apart from each other as they can. That is their most stable arrangement, when they are farthest apart. Okay. Now these domains, there are 4 different kinds. There are single bonds, double bonds, triple bonds, and lone pairs. Each of those counts as one single cluster of electrons, and it sort of behaves like a unit, and it tries to get away from all the other clusters of electrons. So let's start out with CO2. The carbon here has 2 double bonds on it. Each double bond counts as 1 electron domain. So the carbon has 2 electron domains. They try to get as far apart from each other as they can, and therefore the best way for them to do that is to be at a 180-degree angle from each other. Okay? In the Lewis structure here, that is how they are drawn. So this Lewis structure, that's 180 degrees, that Lewis structure is going to be the same thing as the 3D structure because that bond angle is already written correctly. That bond angle is 180 degrees. If we look at the next one, CH2O, the Lewis structure is there. Again, we're focusing on the central atom. It's a carbon, and that carbon has a double bond, a single bond on the left, and a single bond on the right. So that's a total of 3 electron domains. Those 3 electron domains try to get as far apart from each other as they can, and when they do that, they form this shape right here. Here's one of them. And then the others, in order to maximize the angle between them, are going to have this arrangement. Now all of these angles are the same. Okay, these bond angles are the same. And in this case, the bond angle is 120 degrees. Okay, so this particular arrangement has the electron domains are arranged in what we call a trigonal planar arrangement with a bond angle of 120 degrees. For the CO2, just to back up, that arrangement is called a linear arrangement because the electron domains are in a straight line. For the NO2 minus, again, the Lewis structure is given there. The nitrogen in the center has a double bond, a single bond, and a lone pair. So again, that's 3 electron domains. So those domains are going to behave just like the CH2O. You're going to have the nitrogen in the center. You're going to have the lone pair, which we'll represent like this, just to show that it takes up space. Okay, instead of just being 2 dots right next to the N, we're going to make sort of a little electron cloud to show that it is contributing to the shape of this molecule. Then here's the double bond, and here's the single bond. And again, this electron geometry is called trigonal planar. The molecular geometry for this NO2, however, is going to be called bent, because molecular geometry focuses only on the position of the atoms, not on the position of the electrons. So to examine and determine what the molecular geometry is, you sort of ignore those, you ignore the electron cloud, and you just look at the molecule, and it seems to be in a bent shape. Okay, I'll put that back on. All right, so there's a difference between electron geometry and molecular geometry. For the CH2O, the electron geometry is trigonoplanar, and the molecular geometry is also trigonoplanar because the atoms also lie in a triangular shape, and they're all in the same plane. Let's move on to CH4. CH4, the carbon has 4 electron domains, and when you have 4 electron domains, the farthest apart that they can get is when it makes what we call a tetrahedral electron geometry. And to draw this in 3D, this is what it should look like. That wedge shape that I'm drawing for the bond indicates that the bond is sort of coming out of the page toward you, and this dashed line represents that the other bond is sort of going away from you into the page. The bond angles here are 109.5. And like I said, the electron geometry here is called tetrahedral. If we draw the same thing now, again with NH3, notice that it has 4 electron domains, 3 single bonds, and 1 lone pair. So that one is going to look like this. It's going to have a lone pair. We'll put that on top. Then it's going to have the same kind of arrangement that we just saw. So again, for this one, the electron geometry is tetrahedral, but the molecular geometry, if you ignore that lone pair on the top, the electron geometry is what we call trigonal pyramidal, because the N is sort of like the top of a pyramid, and the H's form a triangle underneath it, like the base of the pyramid. So trigonal pyramidal is the name of the molecular geometry for NH3. H2O, 4 electron domains, 2 single bonds, and 2 lone pairs. And so I'm going to draw it like this. And here is one of the lone pairs that's coming out towards you, and here's the other lone pair which is going away from you. Now here, again, the electron geometry is tetrahedral, but now if you ignore these lone pairs, notice that the molecular geometry is bent again. Okay? So the molecular geometry is bent, but the electron geometry is tetrahedral. So that's an introduction to drawing 3D structures using VSEPR. Thanks for watching.